This will be our third momentum video. It's over Newton's third law, and this should be a review from forces, but here we're going to talk about how Newton's third law behaves with collisions. So during a collision, it happens between two objects, and we should remember from our unit on forces that they have equal and opposite forces. So, for example, if you were standing on Earth, the Earth is pulling on you and you are pulling on it. Each of you have a gravitational force, or you're pushing on the Earth and the Earth is pushing back on you, so normal forces. Each of you have a normal force acting on each other. But these forces occur in pairs, and they act on each other. So the easiest way to write this is just say if A acts on B, then B acts on A, and they're equal and opposite forces. And any force that occurs is between two objects that are interacting with each other. In some way, shape, or form, if you have a truck crash into a wall, those two objects are interacting with each other. So any force occurs when two objects are in an interaction. So our first example that we're going to use today is we're going to use an 18-wheeler, and the 18-wheeler is going to be driving down the road, and then there's going to be a fly flying down the road, and they are going to come in contact with each other. And most of you have seen this before. The fly does not win. He ends up on your windshield. But we are wondering which one experiences a greater force. We should know from Newton's third law that each of them have an equal and opposite force, but they are going to have different accelerations. And this happens because of their masses. The 18-wheeler is a very, very large mass, and the fly is a very, very small mass. So they're going to have very different accelerations. The truck is not going to change its acceleration very much or change its velocity very much, and the fly will change it quite a bit. So they'll have different accelerations because of their masses. So we should know that each of them experience the exact same force. F1 will equal F2, so the force of the truck will equal the force of the fly. So M1A equals M2A. But we can substitute in for the acceleration. Knowing that acceleration equals change in velocity over time, we can substitute that in for acceleration on both sides of the equation. And since both of them occur in the exact same amount of time, it's not like one object's in contact with the other object for a longer amount of time. It's the same force, same amount of time. Then the times will cancel. Knowing that the times cancel allows us to recognize that mass times change in velocity equals mass times change in velocity, which shows us that the momentum, or the change in momentum of object 1 will equal the change in momentum of object 2. So the objects also experience an equal and opposite change in momentum. Their forces were equal and opposite, and now we know that their change in momentums will be equal and opposite. The important thing about this is that we have to understand that the magnitude of each of these change in momentums will be the same, but they may not be equal as far as negative or positive. So if object A loses momentum, then object B will gain the same amount of momentum. It's kind of like energy in that sense. You can't lose energy, but you can transfer it. So we're basically transferring momentum from one object to another. So we're showing in this equation right here, back it up a couple steps, that the lost momentum by object 1 we're representing with a negative, so the negative change in momentum by object 1 will be gained by object 2, so it'll change momentum by that amount. So it's not technically lost, it's more like of a transfer idea, but the lost momentum by object 1 will be gained by object 2. So we have negative m1 change in velocity 1 equals m2 v2, change in velocity 2. Now we know that the change in velocity is final minus initial, but in this case, since we're having a collision, our final will be after the collision and our initial will be before the collision, so we relabel them. So instead of them being v minus v naught, we're now going to relabel them as v prime for after the collision and v as before the collision. It makes things a whole lot simpler since we're talking about collisions to kind of locate them as v prime and v. So we now have m times v1 prime minus v1 is going to equal m2 times v2 prime minus v2. we distribute the masses on both sides of the equation. So we have m1 v1 prime plus m1 v1 equals m2 v2 prime minus m2 v2. And that initial mass of mass 1 is also negative. So you can see our negatives, and we have a negative sign at the beginning, we have a minus sign on the after the side of the collision. And now what we're going to do is we are going to move some things around. We're going to add m2 v2 to both sides. And we're also going to add m1 v1 prime to both sides. So we get the primes on one side and the non-primes on another side. So we're trying to get the primes on one side and the non-primes on the other. And with m1 v1 plus m2 v2 is going to equal m1 v1 prime plus m2 v2 prime. This is very nice because what we end up with here is an equation for collisions where we have the initial momentum of each object and the final momentum of each object on the other side of the equation. And it shows us that we have momentum conserved. So this is the conservation of momentum equation that we are going to use. We use these for all types of collisions. That could be elastic, inelastic, perfectly inelastic, even explosions for that matter. So what happens is the total momentum of the system never changes. And this is all from Newton's third law. And so the deal with it never changing, it kind of has a caveat. As long as there are no external forces acting on the objects or acting on the system, then the momentum of the system is conserved. If it's an internal force, it's fine, but an external force it will cause the momentum of the system to change. So the momentum of the system is conserved as long as there are no external forces acting on the objects in the system. So let's continue with this and do an example. So a conservation of momentum example, and we're going to have collisions between two objects. Our first object will be a 2 kilogram object, and it'll be traveling at 10 meters per second square, or 10 meters per second. And our second object will be 4 kilograms, and it will be traveling at 0 meters per second. They're going to collide, and in this case they're going to stick together, and we know this as a completely inelastic collision. Some people call it a perfectly inelastic collision. Either way, they're basically saying the same thing. So we're going to have two objects, one of them in motion, one of them at rest. They're going to collide and stick together. So we have our momentum before the collision, and then we have our momentum after. So we have initial and final. M1 v1 plus M2 v2 is going to equal M1 v1 prime plus M2 v2 prime. Now, in this particular situation, we have to combine the masses of the two objects. So I'm going to show that here where it's M1 plus M2 in parentheses, and they're going to have one final velocity, where in this case V1 prime is going to equal V2 prime. They're going to be the exact same velocity because both objects are traveling at the same velocity. This is the after the collision for a completely inelastic collision, how we set up the after side. If it was just a regular inelastic collision, we would leave the equation as is. So then we go ahead and fill in the initial side, M1 v1 plus M2 v2 equals M1 plus M2 in parentheses times a final velocity. So now we're going to plug in all our numbers. We have 2 times 10 plus 4 times 0, which is going to be 0, is going to equal 6 times the final velocity of both objects. We end up with 20 equals 6v, and divide both sides by 6. And the final velocity will end up being 3.3 repeating meters per second. Now we are going to continue with the idea of conservation of momentum in class and do several different examples, which I've already mentioned. We'll have elastic, inelastic, completely inelastic, and then we'll also deal with some explosions. All of them with internal forces, no external forces, so we can have momentum conserved. And then at that point we will practice quite a bit. So I look forward to doing all that with you in class.